Hey everyone, welcome back to MLworks. In this video, we'll understand what is knowledge distillation and we'll look at the code changes that you have to make to ensure that knowledge is distilled from a larger model to a smaller model. So let's get started with the basic definition of knowledge distillation. So it is a technique that will help you to transfer the knowledge from a large model to a smaller model because large models are capable of understanding much more refined data's pattern, and we can share that knowledge with the smaller model while ensuring that the smaller model remains small, and also we are able to deploy that in much less powerful hardware, right? So we can do that with the help of smaller models. So there is something called as a teacher student model under knowledge distillation, where the teacher model is called as the larger model and the student model is called the smaller model. And basically what happens, right, we improve the accuracy of your smaller model with the help of teacher model, which is the larger model. And while doing so, we only modify the weights of the student model. We are not doing anything else, like we are not adding parameters to it, or we are not adding increasing size of the model or anything. So we are just updating the weights of the student model such that it is performing better than before. Before means without knowledge distillation. So with that, we'll jump on to the Torch implementation of knowledge distillation, and there is this official implementation by PyTorch, which you can go through and go in depth in terms of different ways of knowledge distillation and different aspects that you can change in knowledge distillation. So let me go to the notebook. So this is the notebook here. So what we'll start off with, first we'll import the packages and we'll download the data set, and then we'll be creating a teacher model, which will be a larger model, and then we'll create a student model. Okay, now the student model will not be learning anything from the teacher model initially, and we'll be seeing the performance of the student model initially. Okay, so once that is done, we'll be then implementing knowledge distillation. We'll understand what changes we have to do and why we are doing that changes. Okay, and then we'll be creating a student model along with the knowledge distillation and see if there is any performance improvement or not. So let's get started. So I will not be running the training the job, training the model again, because it is little time consuming. So we'll just understand the code, what changes we have to make, and we'll see the messages, like what happens when you run the code. Okay. So initially what we do is we import all the packages. Okay, first is Torch, then neural network, and then optimizer, and then is transforms, which will do pre-processing on top of your images, and then data sets from where you will download the data set. And then we try to use the device. If you have GPU, then you can set the device as torch.accelerator.currentAccelerator.type. Otherwise you can just use CPU. Okay, so this will give you just import the packages and select the devices. If you have GPU, it will be CUDA, otherwise it will be CPU. Okay, so next step is we create pre-processing step, which is like to transform your input data into a tensor and then normalize the data with these values. Okay, so these are nothing but you have color 3 channels. Okay, this is the mean across the 3 channels. Okay, and this is the standard deviation across the 3 channels, and we apply this normalization on top of your images. So we'll be using the dataset called Cypher 10, which is 10 classes, and you can see the image here. So these are the 10 classes we are talking about. Some of the animals, some are like vehicles. Okay, so this is the dataset. Now we'll use Torch data loaders to transform your dataset into train loader and test loader, and then comes the part of, okay, here also, like, let me just explain what happened here. Batch size is 128, so every iteration 128 images will be picked from the train loader, and we are shuffling the images, and we are using num workers is equal to 2. So there will be 2 workers will be used for fetching the data set. Okay, similarly for train loader, test loader as well. So let's jump on to teacher model class. Okay, this is our first convolutional neural network, where we have 4 layers, conv 2D, conv 2D, conv 2D, conv 2D, and we are performing ReLU, that is the activation function, and then we perform max pooling 2D. Okay, and then we have these are the feature extractors for us. Okay, and then we have our classifiers, which will be like linear to phi12 ReLU, then dropout, and then we have our final linear layer, which will transform your phi12 into num classes. Num classes is nothing but your 10 neurons at the end. So see, this is the forward pass. Okay, we'll first extract the features, then flatten it, and then pass it to the classifier. Okay, so this is the deep neural network, the teacher model, which has 4 convolutional neural network. Now, this is our student model. Okay, here we have 2 convolutional neural network, and then there are 2 activation function and max pooling, and similar classifier. Okay, the only thing, right, if you see the number of parameters, if you see here, it is 3 into 128, 128 into 64, 64 into 64, 64 into 32. And then finally in the classifier layer 2048 to 512, 512 into 10. But here if you see from 64 we are coming to 16, 16 into 16, 1024 instead of 2048 we have 1024, then 256 instead of 512. It's like reduced by half here totally. Okay, so this is the student model here. So basically this is what it looks like. Okay, that student and teacher model. Here we have more number of convolutional layers and almost similar. The classifier remains the same. Okay, and next is the training step. Okay, this is how the model will get trained. So you have first criterion, which is the cross entropy loss. Since you are having like multiple class, we use cross entropy loss here, and then we use the Adam optimizer for updating the weights, and this is in the training mode. Model is in under training mode. So here we start off our epochs. Okay, so this is the number of times the model will go through the data set epochs, and running loss is equal to initially it is 0, and then we have our train loader. So here what we do is we take the input and the label and pass it to the device, which is GPU, and we initializes everything to 0. Okay, the gradients are 0 for every batch. It will be what reset to 0, the gradients, and then we calculate the output here from the model, and then whatever the output we have, we get the loss. Okay, criterion is nothing but the cross entropy loss, and then we go back propagation, and then there is weight update. Okay, so at the end we get our loss, we accumulate it in the running loss. Okay, so this is the whole training step. And if you see here, this is training step, and when it comes to testing, what we do is we again put our model to GPU, and then we are in evaluation mode because we are not going to update the weights. Okay, we'll be just doing the inference. So our evaluation mode is on here for the model, and we are just initializing correct and total, and we have to do the inference like this with torch no grad because we don't want to update the weights. So we fetch the input and labels here. Again we put it to GPU where the model is stored, and then get the output, and we get the maximum probability for particular sample and get everything, right, whatever the size here we have. This is just what calculating the accuracy for accuracy purpose, right? We're calculating these things, and at the end we return the accuracy here. Okay, so that is testing model. Now we have talked about teacher model, which is containing 4 convolutional and multiple max pooling, multiple ReLU. So here we set the, if you want to repeat the same, reproduce the experiment, you can set torch.manual seed 42 and do this specific, initialize the deep neural network with 10 class and pass it to the model, pass it to the GPU, and then here you train the model where you pass epochs as 10, and then learning rate as 0.001, and device is GPU. This is your data set, and this is your neural network. And here we are performing inference. Okay, test loader. Okay, so what happens, right, when you're running for 10 epochs, you are started seeing like epoch loss getting reduced, okay, continuously from 1.32 to 0.11. Okay, and the test accuracy was 75.04. This is for the teacher model. Now comes the light model, which is the student model, where you are initializing 2 times. One will be using it for with knowledge distillation, the other without knowledge distillation. So we are initializing the same manual seed 42 for both the light models, and the classes are 10, again same cipher 10, right? So we have 10 classes and passing it to device, which is GPU. So these two are initialized the same way. Okay, there is no change in terms of what the weights are there. So this is what it looks like. Okay, for both the smaller models, it's the same weights. Okay, for the first layer. Now let's understand the difference between the parameters, right? Number of parameters in the teacher model and the student model. So it's almost more than 1 million parameters in deep neural network, and the light neural network has 2,67,000 something parameters overall, which is like 5x less. Okay, so what we do here is we do the student training and we again run it for 10 epochs, same learning rate, same device, which is GPU, train loader, and light neural network. Now if you are doing the test also again here, so we start off with 1.4 loss for one epoch, and then it continues to go down 0.055. Okay, and the accuracy is 70.48. This is for the student model, okay, which has not in touch with teacher model, okay, right now, and it is giving this kind of accuracy, which is 70.48. Now let's understand, right? Like we compare the performance of teacher and student. So teacher model was giving us 75.04 and student model gave 70.48% accuracy. Now what we'll do, right now, since we have our trained model, which is teacher model, we'll use its knowledge to train a student model and gain the patterns which teacher model has learned and use it with student model. So what we are doing, right? So let's understand how we have to run this knowledge distillation. So we know large neural network, be it like teacher model or student model, at the end what we get is probability distribution over our classes, which is 10. Okay, so the final layer will have the same number of output neurons. So the method works by incorporating additional loss into the traditional cross entropy loss, which is based on the softmax output of the teacher network. So while training the model, we are using cross entropy loss. Now to run with the knowledge distillation, we also have an additional loss called as softmax, which will be the output of softmax output of the teacher network. Okay, so we'll be adding a new loss also. So the output activation properly trained teacher network carry additional information that can be leveraged by student network. So we have our teacher network. It will give us some final output, which is the probability distribution across the classes. We'll use that information and create a new loss and use that loss along with the student loss, which we perform traditionally like cross entropy loss. We'll add them together and then update the weights. Okay, so let's understand that again, right? So why softmax, which is the full probability distribution output by a teacher model, can be more useful than hard target, such like the class label. So normally what we do, right, while training the model, okay, so we say this specific class is there, 1, the other class are turned into zeros. Okay, mostly that's how classes are represented, which are like the hard targets. So instead of that, what we do, right, we'll be using the probability distribution across the classes. For instance, okay, here you can see truck has the probability of 0.8, automobile has 0.15. This is for a specific image. This is the probability score. Okay. Now, even the low probabilities assigned to the incorrect classes in the teacher model's output can reveal useful information. Okay, so these small values help express how the teacher understands relationship between the classes. So this is an output for an image containing truck image. Okay, so the teacher model was able to, with the probability distribution of 0.8, it said that this is truck. With the probability of 0.15, it said it is automobile. With the probability of 0.04, it said it is airplane, and there is 0.01 probability it might be dog. Okay, this is a very less value, and these are like almost, they all come under vehicle actually. Okay, so teacher was able to establish a relationship between the classes. Okay, and it has able to understand that information. Okay, these are like they belong in the same feature space, these three things, first three, and this belongs in a separate feature space. So this shows the teacher believes the truck image is somewhat like an automobile or an airplane, but very unlikely to be a dog. These relative similarities, the ratios between small probabilities, help shape a richer learning signal for a student. So we'll use this information of probability distribution, okay, and use it for the student network, and it will learn better patterns from the images while training. Okay. So deep networks aim to map similar inputs, okay, trucks and cars to similar representation in the feature space. And the soft targets help these two because they encode class similarities, just not right and wrong. So when we use soft targets like probability distribution, instead of just labeling it as zeros and ones, when you use soft targets like probability distribution, it gives you the class similarities instead of just giving what is right and wrong. Okay. So just instead of saying this is a truck, the teacher says this is mostly a truck, or a bit like a car and a very little like a dog. This giving the students a sense of how to think about the image. Okay. So this is a very important point actually. Okay. So why we are using soft target along with the traditional cross entropy laws. So cross entropy laws used for hard labels focus only on making the correct class probability high, ignoring the rest. Okay, the probability of other incorrect classes are squashed down to zero, and the gradients for these tiny values don't affect the weights much. So if you are just using hard labels, it is quite difficult for learning for a smaller model. That's why the class probability is quite important. So the model doesn't learn the structure of relationships between the classes as effectively. Okay. So let's understand the conclusion, right? Like soft targets, okay, which is the loss that we get from a teacher model. It carries an extra information about how the teacher understands the relationship between the classes. These subtle signals, even in the small probabilities, help guide the student model to learn more than just correct labels. Okay, so standard cross entropy ignores the richness, which is why knowledge distillation works better with soft and output distribution. So that's why we are using soft distribution, probability distribution coming from teacher network along with our traditional cross entropy laws. So we'll understand that here. Okay. So we'll understand the code, how changes we have to make such that it runs. So for the teacher network, it is the same thing. Okay, the network is similar, but while training, okay, the loss that is getting generated or the logics that are formed at the output layer for the 10 neurons will be used along with the student model, the loss created by the student model, along with the cross entropy loss that we have here. We'll use this loss along with this loss to train the student network. Okay, this is already a pre-trained model now because we have already trained the teacher network and we saw that it is 75.04% accurate. Now let's understand how to do teacher-student training. So it contains actual labels, okay, for normal training, which the student model goes through, and we have this teacher model which will give the softened prediction, which is the probability distribution, which wrong classes are still somewhat likely, subtle patterns the teacher has learned. So this will give us the information of these two aspects. Okay, and this approach helps the student model perform better, especially if it is smaller or less powerful. Okay. So we understood this part, right? So we are going to add a new loss function and then combine it with the existing the normal loss function, which is a cross entropy, and then we'll train the model in such a way. So yeah, so this is the function for train knowledge distillation, where we are initializing the cross entropy loss, and there is optimizers, which is Adam optimizer again, and we are using teacher in an evaluation mode and student in a training mode. So since we don't want to update the weights of teacher model, we are putting it under evaluation mode, and student model we are putting it under training mode. Now, so one more thing right here, importance, right? One more thing which is here you have to understand is the weight, soft target loss weight and cross entropy loss weight. This is the amount of weightage that is given to the loss function, right? So this is what is being used. This is 0.75 if I'm not wrong. Okay, and this is 0.25 for soft target loss weight 0.25. So what it means, right? We are giving more weight to the cross entropy loss and less weight to the soft target loss. Okay, this is that. This is 0.25, this is 0.75. Now again, this is similar to what we have done earlier. So we are iterating through the epochs and running losses 0.0. Now we have our for inputs comma labels in train loader. We take the input and labels, put it into the device, and then reset the gradients before the next backward pass happens. Okay, so here if you see, we are not updating the weights of the teacher model because we are running it as with torch.no gradient. So we are just getting the final logits, which is the 10 neurons, okay, and getting it here. So if you want to understand, this is a forward pass with teacher model. Do not save the gradients here as we do not change the weight, teacher's weight. We stop the gradient updates since teacher model is already trained. Passes the data through the teacher model to get the predictions, which is the 10 logic values. This is forward pass for the teacher model. This is the forward pass with the student model. And here we are updating the weights. Okay. So this is the next way of calculating softmax. Okay. So here if you see, we have parameters like T, temperature, which is for smoothizing the logits value. And there is teacher logits, which is soft targets probabilities. And then we are performing log softmax for the student logits. Okay. So this is what we get here. At the end, we'll have 10 values here. Okay. And probability scores that too. Next, what we do is we compare these two. Okay. So we are performing something called as KL divergence. How much these two distributions of logits differ. Okay. This will give us the soft target loss. Okay. This is the function for this. So if you see here, compute a loss based on the difference between teachers' soft targets and students' log probabilities. This is similar to KL divergence, how one distribution differs from the other. Okay, so this is what we do. And there is something called as multiplied by T square, which is recommended by the paper. This is based on the paper, we multiply T square, which is the temperature. Okay, so we get the soft target loss. Okay, which is based on soft target plus soft prob. Okay, so this is that. And this is again the loss function. Okay, this is the cross entropy, which we normally do. Student logits against the labels. And then what we do is we combine these losses. Okay, so label loss and soft target loss. And the amount of weightage that should be given to these loss. Okay, so if you see here, soft target loss is into multiplied by the soft target loss weight, which value is 0.25. So it will be given less weightage. This loss will be given less weightage. And this weight, which is cross entropy loss, okay, which is 0.75, and its corresponding loss, label loss. Okay, it will be given 0.75 value. Okay, the more weightage is given to this specific loss. Now, then we combine and get our final loss. Okay, and then what we do is we do something called as loss.backward to update the back propagation, and then we update the parameters here. Okay, and then we keep accumulating the running loss. And we just print the epochs and corresponding loss here. So if you see here, train knowledge, then we pass our neural network, which is deep neural network. Okay, the student model, teacher model. This is the student model, lighter version, which was not trained. And then we pass the data set, the epochs, learning rate, same, temperature is 2. And the weightage that we are giving for the soft target is 0.25. And the weightage that is given to the cross entropy is 0.75. The device is CUDA. And after running it, we can see here, okay, from we start off with 2.3 as the loss for first epoch, and then it reduces to 0.91. The test accuracy is 70.65. This was the student model that we saw earlier, 75.04. And without teacher, we got 70.48. And with teacher, which is the knowledge distillation along with cross entropy, we get a slight improvement in terms of 0.17 in terms of accuracy. Okay, so this is in terms of what, since the model is also what actual teacher model is giving just 75%. Okay, the knowledge it has learned, it has merely improved the model. If the teacher model was very good, like if it was giving 95% something, there is a very good chance that with knowledge distillation, you will be getting much more higher percentage. Okay. So I hope you have understood what are the changes that you have to do in terms of knowledge distillation while training a knowledge distillation model. Okay. So with that, I'll be concluding this video. Thank you for watching.